Let's talk about a plane. You're used to working with planes all the time. For example, if you're working on a table or a desk, that desk is most likely flat, unless you're my table, which has kind of a slight warp in it. So that flat surface has two dimensions. And those two dimensions you could consider to be rectangular. We could call one dimension the y-axis and one dimension the x-axis. Now, when you put things on that tabletop, let's say you might place a bottle. For me, it'll be wine. For you, it might be water. So we place a bottle on the tabletop. That bottle has an axis that is perpendicular to the tabletop. Let's say now we place just a ball on the tabletop. That ball has an axis that can also be considered normal or perpendicular to the tabletop. Let's say we connect those two things, the bottle and the ball, with a vector. That vector lies in the plane because both the bottle and the ball is in the plane, and we could construct a line normal to the plane. And since the vector that we drew from the bottle to the ball is also in the plane, that line that is normal to the vector is also normal to the plane. Let's say we have another object on the plane. Maybe we have a paper clip. And let's say we have an eraser. And we connect those two objects with a vector. Well, that vector lies in the plane because the paper clip and the eraser lie in the plane. And there's a vector that is also normal to the vector we drew from the paper clip to the eraser. And since that vector is normal to the vector between the eraser and the paper clip, that vector must also be normal to the plane. Well, let's take a look at this. Let's look at any pair of points lying on our table. So this might be between some pairs of points there. Here's some pair of points here. Well, actually, triplets of points. I'll have a point in the middle and I'll have these 2 points out here. Let's look at some other points there. Some other points here. Now, as I'm drawing this on my screen, all of these vectors lie in the plane, in the two-dimensional surface of the screen that I'm writing on. So all of those two vectors, since they lie in the same surface, they lie in the same plane. Now here's the thing. With all of those vectors, there is a vector that is normal to them. So here's a vector normal to the vector in the plane in that direction. Here's another normal vector. Here's another normal vector. In fact, there are an infinite number of normal vectors that are perpendicular to an infinite number of vectors that lie in this plane. This suggests a way of defining a plane. And to see it, let's change the orientation of our plane. Let's say our plane is oriented like this. And let's once again look at 2 points. One point we will call P naught. The other point we will call P. These 2 points lie in our plane. If we connect a vector between those 2 points, we will label this vector P naught to P. Notice, and let's actually create another vector. And in fact, let's call this first vector P1, or at least the point that the vector ends on, P1, and let's look at another point, P2. And let's connect a vector from P0 to P2. And this vector we will just label as P0 to P2, and the first vector we will label as P0 to P1. Those two vectors lie in the plane, and notice there is a vector that is perpendicular to both those two vectors and to the plane itself. Well, let's take a look at this. In this picture of the tabletop, notice there are a number of different vectors we could draw between the objects on our table, and those vectors are not only normal to the table, but they are also parallel to each other. That's not how you spell each other, that's a mashup. So we will say each other here. Same thing in this image right here. Same thing is true. A number of vectors are in the plane. They each have a vector that is normal to them and normal to the plane, and all of those vectors are parallel to each other. Same thing with this bottom image. We have, and let's go ahead, I'm going to just go ahead and label some of these vectors with a unit vector. Unit normal vector, and let's label this with a unit normal vector. Well, the thing that each of these planes have in common is that they can be described by two vectors in which those two vectors have a normal vector, or we could say two different normal vectors that are parallel to each other and are also perpendicular to the plane. So this suggests a way of defining a plane. Let's now look at the definition of the plane. Given a fixed point P0 and a non-zero normal vector n, the set of all points P in three-dimensional space, so I will have a point P here, maybe a point P here, point P here, point P here, point P here, point P here. The set of all points P, so each of these points, that might be P1, P2, here is the nth P. Given a fixed point P0 and a non-zero normal vector n, the set of points P in three-dimensional space R3, for which P0 P vector is orthogonal to the normal vector, is called a plane. So in other words, these points can't just be any points in space. They must be points in which, when we construct a vector from one point to the other point, the set of all vectors that we could construct such that they all have, such that this normal vector is perpendicular to each of those vectors we construct, would mean that all of these vectors lie in the same plane. So we can actually define a plane just like this. And notice how the plane is really defined by the unit vector, or by the normal vector that is normal to each of those vectors in a plane. And to have this definition work, we're going to be able to see that all we need really are 3 points in the plane, or 3 points in space to define a plane. 1 point 2 points, 3 points. And with these 3 points, if we construct 2 vectors for those 3 points and look at a vector that is normal to those 2 vectors that we just drew, the plane in which those 2 vectors lie can be described with that normal vector. So this is how we are going to proceed with our definition of the plane. So again, we just need a fixed point, a non-zero normal vector, and a set of at least 2 other points for which, when we construct vectors between P naught and the 2 other points, the normal vector is perpendicular to each of those. So here is an illustration of a plane such that the plane is parallel to the XY coordinate plane. In this image, notice that there are 2 points. So really just those 2 points, they don't define the plane. We'll need at least 3 points to define this plane, but for this illustration, it's just illustrating an arbitrary point, or 2 arbitrary points. And in this illustration, it's showing a vector that is normal to both the plane and the vector those 2 points lie in. If I were to redraw this picture, I would redraw it like this. Here is our x, here is our y, our z-axis will be vertical. We are taking a plane that is parallel to the xy plane, so let me draw that plane parallel to the xy plane, and we could uniquely determine an equation for this plane by knowing a point in the plane and by taking 2 other vectors in the plane. So I'll just call this again P1 and P2, and we can construct vectors between P1 and P2. And then a vector that is normal to both P1 and P2 will also be normal to the plane. So then the task is, let's see if we could come up with an equation that uniquely describes a plane in space. If we were to guess what that equation would involve, we should guess that it would involve a normal vector. And that normal vector must be perpendicular to 2 other vectors in the plane. We also need a point in the plane to help us describe an equation of a plane. Here is the standard form of an equation of a plane containing a point, P naught, and having the normal vector n. So notice this equation of a plane. This equation of a plane is not a vector equation. However, this equation contains information about the normal vector, and it contains information about at least 1 point in the plane. Let's look at this. the standard form of the equation of a plane containing the point P naught and having the normal vector n equals, and the components of n are a, b, c for the x, y, and z components respectively, or rather the first, second, and third components respectively. This standard form of the equation of the plane is given by the first component of our normal vector times the difference between our point P in the plane and our point P naught that is known in the plane, plus the second component of our normal vector times the difference between the y coordinate of point P and the y coordinate of point P naught, plus the z component, the third component of our vector in the plane, times the difference between the z coordinate of another point in the plane and the z coordinate of our P naught point in the plane. Let's write that over here. So the equation of a plane in standard form is given as A, the x component of our normal vector, times the difference between 2 points, plus b, the difference between the x coordinate of 2 points, plus b, the y component of our normal vector, times the difference between the y coordinates of 2 points in the plane, plus c, the z component of our normal vector, times the difference in the z coordinates of our point in the plane, and this must sum to 0. Notice that the coefficient in front of each of the differences in coordinates, this coefficient defines the components of our vector normal to the plane. So our vector normal to the plane just has to be non-zero, doesn't have to be a unit vector, but our vector normal to the plane has components a, b, and c. P naught is a point in the plane, so P naught has coordinates x naught, y naught, and z naught. And then P is just some arbitrary point that lies in the plane. Again, if we can construct a vector between any pair of points or in our plane and have a vector normal to the plane and normal to that pair of points, we can come up with an equation of a plane in standard form.